Thank you everybody for coming. Just to give you a quick introduction, well, my internet name is iPadX and I do stuff with sounds and video game consoles. And today I'll talk about something that you'll see in a second. Okay, so at least hope perhaps some of you might have seen one of those games before. And of course it was as a quick demonstration of the music that's playing the games, because as you might have guessed from the title, it's about music, it's about the GBA, the Game Boy Advance, the successor of the Game Boy. And I want to talk to you about today, how does the music on the system work? How do game developers make sound? What are the challenges and what characterizes these sounds? So yeah, let's get right into it. I try to divide it into these three parts. We'll talk about hardware, software, and emulation, because I think each of these topics kind of deserves its own point. Yeah, hardware, I mean, you've probably seen it before, I hope so at least. This cool console here. Well, I already said it was a successor to the Game Boy. And comparatively, it was quite upgraded. It had a 32-bit CPU with 60 megahertz, so that was quite an improvement of the old. And I mean, it had very much improved graphics, so it was the game developer's dream, so to say. And one of the very new things on the Game Boy Advance was that it could do stereo PCM sound. So PCM would be sampled sound, like essentially you could play back anything, not just these beep, boop sounds that you might know. And one interesting part is that the Game Boy Advance would be backwards compatible. And we'll get into why that's important later. Okay, so just to give you a quick overview about how the hardware looks like. So we start up with this ARM7 TDMI CPU core. Internally in the system, it is just connected to a bus because, well, at least one thing that makes the CPU very much easier to handle than the Game Boy is that there is no longer any need to deal with memory banking or anything, because all the memories that are large and they're just connected to one bus, and you can just directly access them by just using the right address. And I mean, you have some stuff here. I try to color the stuff that's not on the SoC itself in blue. Not super important for what I'm talking about, but yeah, we have two RAMs and we have the cartridge memory, which is of course 32 megabytes, is greatly improved over any Game Boy game you would know. And there's a bunch of peripherals in there, like the stuff that you see in the bottom right. It's not so important, so that's why I'll grey it out, at least not for today's talk, because what we'll worry about is how does the sound work. And you could already see there's still a bunch of the peripherals are still visible in there. So we have an interrupt controller, we have a DMA controller, we have timers, we have a sound controller. Well, I mean, that's kind of obvious, right? And there's also BIOS memory. So what's up with the BIOS here, we'll also see later. Okay, but let's first talk about the very obvious stuff. There's a sound controller in the Game Boy Advance. What does it do? And why do we need possibly other peripherals? Let's check. Okay, so we start out with the programmable sound generators. Those are mostly the same as found on the Game Boy, and I believe, I mean, the Game Boy Advance was backwards compatible, so they already had the sound circuit of the Game Boy in there, so you might as well just recycle them. And essentially what you have is these four programmable sound generators, two square wave generators, which are mostly identical, except that the first one can do like frequency sweeps, which can do sounds like this. Might have heard before, or just regular like melodies. Yeah, that's we'll have to deal with the sound. Anyway, so I mean, it's kind of what you would expect from a Game Boy, right? And there's also this little wavetable sound generator where you could load very tiny snippets of 4-bit samples in there, which would make it somewhat usable to make more flexible sounds, but it's still somewhat limited. So these would all be sounds that you can make with this generator. And there's of course a noise channel, which you might have known from like the way that you would make like rhythms and percussions or noise sound effects. Okay, so but that's the Game Boy stuff. Perhaps you may know about. It's pretty straightforward. You feed them, well, one additional feature is that you have some way of controlling volumes on these. You have envelope generators like you'd have on your synthesizer, except that they're pretty bare bones. They're not like, you don't have ADSR curves or anything. They're pretty simple. And for some reason on this third channel, the PSG wave channel, they didn't add one. They just have a static gain control. I have no idea why. Ask Nintendo. But what's new in the Game Boy Advance is the stuff that you see here. You have 2 PCM channels that can play back sampled sounds at 8-bit resolutions. That's what the S8 means. And it goes into like a rudimentary mixer. It's not like not a very super flexible mixer. Like it's mostly like you can turn stuff on or off and it adds things together. Nothing really else. So you wouldn't able to like smoothly control volumes of the PCM outputs. This is nothing that this mixer can do, but it gets the job done. And of course, you can play back anything that you like with these PCM channels. For example, something like this. Oh, I hear someone knows what it is. Good job. And then basically, once it comes out of this mixer, it just goes into a digital analog converter. It's a pretty bare bones DAC, like it's just a PWM controller, but it gets the job done. It's not super hi-fi, but yeah, it works. But one thing is now, of course, like if you go back to this slide here, the way that you would control these programmable sound generators is that you just essentially write a couple of registers that turns the tone on or turns the tone off, changes the pitch, whatever. But how do you really do this with PCM? Because you kind of need to send a stream of data in there. How does that work? Well, of course, usually this stream has to come from somewhere. And usually that would be ROM or RAM. Oh, well, most of the time it would be RAM because you would generate this on the fly if you don't want to just play back a single static sound. Because, well, as you can see, you only have 2 channels. And if you cannot really control volume or anything, well, I mean, it gives you 2 channels to make stereo sound, but if you want to play back multiple sounds at the same time, well, you're out of luck. So you essentially have to do some processing in the software, which means that you play back stuff from RAM. But how does it get into the PCM output? Well, there's a FIFO circuit, which can buffer 32 samples, which coincidentally means 32 bytes, because we have 8-bit samples. But how does it get there? And how does it get output? Well, I mean, essentially what you need is to set up a timer, and this timer then tells the FIFO to, every time the timer overflows, to output 1 sample to the hardware. But of course, at some point, this FIFO will run empty, and you need to refill it. How does that work? Well, you have a DMA controller, and this is kind of how we program a microcontroller. You set up a DMA to read from one location and to write to another. But you, of course, need some kind of mechanism to trigger that. And what actually happens is that every time the FIFO runs empty, you can just set a bit to do that, that it will request new data over the DMA. And that's pretty straightforward, right? It gets data from RAM and puts it into the FIFOs. The only problem with that is, like when you program your microcontroller, you may know it that, well, I mean, you kind of set your memory addresses and how many bytes you want to transfer. And then perhaps you set up an interrupt to receive a signal like when it's done. The only problem is on the GBA, there's no really way of knowing if your playback is complete or not. And that is kind of a problem, because if you set up an audio buffer and you don't really know when it's finished playing it back, so what do? You have to kind of come up with a solution to that. And because, of course, we have to know, because if we want to play back continuous sounds, we have to rewind the DMA to start from the beginning. And so how do we do that? Well, there's unfortunately not really a nice solution to this. One thing that you can do is just set up a second timer that kind of measures how the time that has been passing since the playback has started, and then trigger an interrupt exactly at the right moment. So I mean, like cycle accurate, to be in the right time frame to rewind the DMA. I mean, there's a little bit of a time frame that you have because let's say you have a 32 kilohertz sample rate, and these transfers occur in 16-byte batches. You have about 0.5 milliseconds timing that you essentially have to rewind the DMA. And if you don't meet this timing, well, then you get audio glitches and it sounds ugly. And I mean, you can do that, but the only problem is that it means you cannot block interrupts for longer than 0.5 milliseconds, which you can do. But the thing is, if this happens uncontrolled somewhere in your game loop, and you block interrupts for too long, then you're screwed. Another possibility, which was more common, would be to just rewind the DMA at every V-blank RQ, which is the main interrupt that every game's pretty much had when the screen would be finished drawing. The only problem with this is that this causes new issues, which is that, I mean, this essentially means that you have to synchronize your buffer timing with the V-blank timing, because, well, otherwise you'd get glitches. And that means, I hope that makes sense, that the sample timing must be a divisor of the V-blank timing, because if your sample timing is just ever so slightly off, that eventually the time frame where you have to rewind the DMA would get out of alignment, and then you'd get glitches again. Another disadvantage, this is mostly a quality concern, is that you can no longer integer resample to the digital to analog converter, and that's that's unfortunately a bullet you have to bite. So a quality loss, so to say. And let's summarize these timing constraints. I hope it makes sense. We have a CPU clock of approximately 60 megahertz. That's 2 to the power of 24, just in case you're interested. The V-blank interval is this amount of cycles, and if you divide those numbers, you get around 60, which is the frame rate of the console it's running at. And the problem is now if you also want your sound buffers to have like a 16-byte alignment, because, well, I mean, the FIFO will request the data in 16-byte batches. This, once again, puts some timing constraints on your buffers. And what you end up with is these very funny-looking sample rates. And really, you can only choose one of these sample rates to play back audio if you want it to rewind your DMA at every V-blank RQ. And of course, when you look at this is quite ugly, but essentially this is what all the sound engines that were on the GBA did. Because there are possibly ways around it, but I don't think even in the homebrew community anybody has really managed to find a good solution. And these were kind of the most common sample rates used, which might seem a bit low. It's a lot lower than, like, your CD quality would have 44/100 hertz. This is a lot lower, and it's a bit better than like your phone, but also not really hi-fi. But again, if you remember the soundtracks from the Game Boy Advance games, they have crunchy sounds, so I guess it's fine, right? So, and of course, Nintendo was aware that all of the stuff that we've seen before possibly causes issues for developers, right? Because if you have to get all this stuff right, and basically if every game studio has to deal with it, that kind of sucks. So they came up with this. Okay, so you get the deal what it is. So basically what they would do, by the way, this demo has fallen off the truck and I took the liberty to replace the background. So anyway, so what Nintendo would do is that they shift this sound engine essentially with their SDK. And now you might have already guessed where the title of today's talk is coming from. It's not quite identical to what you see here, but I figured if I write music play AGB 2000, people wouldn't understand what it's, or not so much what it's about, right? So, and I dedicate an entire chapter to this because, as we'll see later, really, without the software, sound on the GBA doesn't really exist. And let's go over a few facts. So it was part of the SDK, so every developer would essentially have access to this. And what it came with is really a very powerful sequencing engine. So you essentially kind of put something like MIDI files in there, and it plays back notes like your, I don't know, your DAW at home. And it would support PCM samples, it would support these programmable sound generators, which would allow you to create soundtracks that have kind of both. And this is really what I'd say characterizes these game soundtracks, that they have these basic sound generators, but still have these still have the sampled sounds in addition. And I think that's pretty unique for a console. I mean, of course, not every game opted to use both options, but there were quite a few that did. Interestingly enough, you might have remembered from the beginning, I showed the BIOS memory in the diagram. Why is it important? Nintendo also opted to include a copy of the sound driver in the BIOS. So the BIOS is essentially just a boot ROM that boots up. Like when you switch on the console, you see the boot logo. And it also provides a few utility functions to games. And Nintendo opted to add the sound driver to the BIOS because it would allow you to create games with a smaller memory footprint. And this would be important for multi-boot games, so games that you would load over a link cable, because they have to fit in memory. So they have to be as small as possible. And they also shipped some authoring tools with it. That's some that you see here. What you'll probably not know, which I'll show in a second. And in addition, also a very powerful API. If you remember the demo from the beginning, you saw the plane flying around there, and if you would be wearing headphones, you would notice that like the sound is actually moving from the left to the right, the pitch is changing, and these are all things that this engine allowed developers to make, which I think is at least from my observation is things that other sound drivers from the time didn't do. And so essentially what you would do as a developer is that you have like this giant text file that you'd feed in a tool called MKS for AGB, which is also why, including me, some people for a while called this engine the M4A engine. Essentially what you write is a giant text file, and what you do is you program all the sounds of your game into there. And you can imagine this process being the same as you have your synthesizer at home, and you would dial in all the patches, how they should sound. This is essentially what you would do here. You'd program all the samples that your game wants, and pretty much that. And they'd also have this tool that's called mid2AGB, which would convert MIDI files, standard MIDI files that you know, to the format that the sound driver needs. And there's also like a sample conversion tool, not too important, except they all function a bit differently and they're odd to use. And essentially what you'd get in the end are object files that you can just link into your game. Well, because there's no file system or anything on the GBA, so you'd link the binary data directly into your game executable. And then once you're done, you just call one of these functions. This is an example, M4A song num start, if you have put in the song number in your authored file, and it would start the playback. So out of a developer's perspective, it's quite easy to use. And I mean, you may not know that, but I for a long time was in the ROM hacking community, and I've came across these tools before, but I realized AIF to PCM and mid2AGB suck, so I revoked them, which you can find on my GitHub page. Also, one thing that I think is fairly unique, which other sound drivers on the GBA didn't do, was supporting playback of multiple songs at the same time. And first you might think like, what is this good for? Like, do you want to listen to multiple music at the same time? Perhaps not, but like essentially what this means is you treat sound effects the same as music playback. and it also allows you to do things like crossfade certain musics, which you otherwise wouldn't be able to do. And over there you'd have your sequencer engines, which would handle all these players and then kind of map them onto a virtual array of channels. And there's a very sophisticated priority system and all kinds of stuff in there. And essentially these, in the beginning we looked at the hardware circuits of the PCM sound. What you see here in blue is completely in software. So essentially we'd have software channels which the sequencer engine would use. And then there'd be a mixing process happening in software, because we only have these two stereo channels that can output to the hardware. So we have this mixing engine. And there's also a sound generator engine which deals with a bit of volume calculation. It is quite complicated, but it also doesn't do very much, but it's necessary. And all the things that we see here on the left are done in software. And this is why I was saying previously, well, what really makes the sound on the GBA is the software, because without the software, you can make some basic music with the sound generators, but essentially, you're screwed. And the hardware portion of that is pretty small. Also because I'm from the ROM hacking scene, I essentially realized this mixing engine, it kind of sucks. It's very noisy and it's slow. Like the developers would have to bite one bullet. Either you'd have a low sample rate, or your game would lag when you use a high sample rate. And most of the time you wouldn't want your game to lag. So what I did is I wrote a re-implementation of that, and I also briefly discussed this in actually my last year's talk here at Winter ICMP, so, well, maybe you want to check that out. Okay, so just to give you an idea, there was really all kinds of sophisticated features in there, and I want to give you an overview. Like, you'd start essentially like with a big song table where all your songs are stored. And essentially, those just have pointers to individual songs in your ROM file. And then you just have some pointers to tracks, and there's like a bytecode in there which encodes like your MIDI file, play back a note, change the volume, change the pitch, whatever. And another thing would be these voice tables that you have, which is essentially like a patch cartridge that you would insert into your synthesizer, which would say, okay, now I have these set of patches that I can play on the keyboard, and these would be attached to one of these songs, and you could have like you could even have songs that use the same voice table just to avoid like data duplication, and like have any type of references that you like. And then, for example, in one of these voice tables, you'd have a reference to sample data that's stored somewhere in memory. For example, a bell sound or whatever. And I think also one of the very forward-thinking ways they implemented this was that they supported nested tables, which of course you think, okay, what's about it? Well, if you know anything about keyboards, romplers, samplers, well, then you may notice that when you play, for example, the lower part of your keyboard, your piano will have a different timbre than when you play it on the higher range. So you want to have splits on your keyboard where you can assign different samples to different ranges. And they supported that, which I think is pretty cool. Which, like, for example, if you write music in your tracker, well, I mean, I guess some tracker formats support that, but the more basic ones don't. So I think that would be very forward-thinking. Okay, I mean, so far so good. Now, one thing more about the BIOS. I already told you that there was a copy in the BIOS of the sound driver, and this would be unfortunate for Nintendo, because it would eventually lead to the first known BIOS exploit of the GBA. And so, just to give you some context, normally the BIOS is read protected. You cannot access it, like when you because they have this very basic, but I mean initially secure read protection, which means your program counter has to be within the BIOS memory region. And so, essentially, only code that's in the BIOS can read the BIOS, which first sounds okay, and for the most part, it is. Unfortunately, it includes a copy of the MP2K, and the thing is, the MP2K the Music Player 2000 was also included in the SDK, so developers already knew what it would look like. And so they essentially had a way of looking at the software and finding exploits without looking into the BIOS first, which is of course lucky, at least for the attackers. And you'd essentially, how you'd interact with this BIOS call, you would just do a ARM supervisor call, like you'd probably already know if you know ARM assembly language. So how was it exploited? Well, there was a function called the MIDI key to a frequency. And also what I should note is Nintendo was very careful about protecting all the functions there were in order to not exploit it. But it was one of the functions that they forgot, and we'll see in a moment why. So what this function really does, it's not super interesting at first look. What you want to do is like when you press a key on your keyboard, you want to calculate at which sample rate to play back your audio sample. And this wave data structure, you'd find this in your ROM. It would have like a frequency value, which essentially means, okay, when you press the middle C, this is the sample rate at which the sample is supposed to be played back. And then you can use this sample rate and the MIDI key that you actually want to play in order to calculate the difference in terms of pitch that you have to pitch it up or down. And if you know anything about music, essentially what you do is that you use a power 2 function, because every time you go up 1 octave on the keyboard, you double the frequency. So that's essentially power of 2. It doesn't matter exactly how it works, but I just thought I'd add it. And this is not how it was actually implemented, because the GBA doesn't have floating point or anything. But yeah, just to give you, for the ones who don't know, like an idea of what this function does, you put in a sample rate, for example, 22,050 hertz. And this would be the default sample rate. And if you would play back a MIDI key of 60, this would get exactly the same number out, because this is the center value of the power 2 function. But for example, if you want to go up 1 octave, which is 12 semitones, then you'd get double the frequency. And for example, if you play a perfect fifth, which is in equal temperament roughly 0.5, a ratio, then you get, well, I mean, close to 33,075. Not quite, but that's why a perfect fifth isn't a perfect fifth. But we don't want to get into piano tunings and that stuff. Okay, so this is a function that was exploited, but how was it actually done? Of course, I mean, this is an exploit. Well, they forgot to check a pointer, which is this WD pointer, and let's go back what it is. This is essentially this pointer that you have here, which is the sample header where this frequency value is stored in. And of course, if this pointer is not checked, what you can do is that this is essentially executed in the BIOS, and it allows you to read memory at arbitrary addresses. Of course, if you first look at it, you see this value is multiplied with some ugly values possibly, so it's not super straightforward to exploit first, because you have to be very careful about the results. So now we will look into how it is actually implemented. So I already mentioned the GBA doesn't have an FPU, it only does integer. But, well, how do you do it without floating point? Well, you use lookup tables, which is, I guess, makes sense. And it's a bit complicated how this is done, because they try to be as memory efficient in this implementation of the function as possible, because they don't have a pitch or a factor value for every single MIDI key. Instead, what they do is that they have this frequency table, which essentially is just a pitch ratio for one single octave, so just 12 semitones, which says by how much to multiply the frequency value. The thing is, then you first have to map the MIDI key to the key within a single octave and the octave number itself. Because if you know the octave number, then the octave just means double or half the pitch. And doubling or half the pitch is easily done with shifting. And so this is how it is implemented. So which I'll show you on this slide here. So what you would do is that you have this MIDI key, which you put into the scale table, which gives you the number of bits that you have to shift the frequency. And then they encoded it in this set table with nibbles in order to be memory efficient. It's not too important. And then they'd also use this lookup table to get the key within one octave by how much to multiply the pitch. And in the end, you get a frequency factor, and then you just multiply. I mean, this is perhaps a bit easier to read now. You just multiply this frequency by this factor and then shift it to 32 to normalize it again. So now we're getting closer. Like, how do we actually exploit this? Well, I mean, this is of course not obvious to see why you have to choose MIDI key 168. It's essentially what it allows you is to get a shift of 0 and a key of 0. And what happens if you choose this is that you get a frequency factor of exactly hex 8 and 7 zeros. And of course, if you know your binary math, this is the same as just shifting 31 bits to the left. Now we're getting closer, but you might already notice something. This allows us to read memory, but unfortunately only allows us to read 31 bits of memory, because if we shift 31 bits to the left and 32 to the right, there's 1 bit that's getting lost. So how do we recover this lost bit? Well, I mean, there's a trick on the GBA that you can do, and this has to do with unaligned pointers. Because I mean, strictly on the old GBA on the ARM or the old ARM CPUs, unaligned reads are not supported. I'm not sure even if they are supported on new CPUs. Anyway, these would not be allowed. But the thing is, the CPU doesn't throw an exception or anything when you do an unaligned read. It just does something. And what it actually does is nothing like a forced alignment or something where it would just discard the unaligned bits or anything. What it would do is like a weird rotation, where it basically, instead of reading the one byte of the next word, if you would increment the rest by 1, it would instead kind of rotate the word around. It's not too important how it works because I'm not going too much into the details, but it's essentially by rotating the read data around, it would essentially allow you to also read the bit that would be originally lost. So this is how the first BIOS exploit was discovered, and I just have to say this: I did not discover this. This has been known for, I think this was like within a couple of years. This was known, probably not even 2 years, I guess, because as I said, the Music Player 2000 was shipped with the SDK, so developers or even attackers that had access to it, they could just throw a disassembler onto it, and then instead of calling the function from the SDK, they could call the function from BIOS and use it to exploit it. Yes, so what did they do? Well, pointer checks, do pointer checking. And the other thing which they were not too smart about is, well, if you want to do security by obscurity, at least do your obscurity right? It doesn't make sense shipping a copy of it if you want to protect it, right? Yeah. So at least I'm trying to get a conclusion, at least out of my perspective, whether this Music Player 2000 was a success or a failure. I'm not sure if it makes too much sense, but in a way, I think it was a remarkably well-designed sound engine. Of course, we've only really touched like very briefly what it can do. But at least for anything that you had before on the Game Boy, it was very powerful. And it was certainly much more designer friendly, because that's a spelling error, ignore that. And compared to, I mean, there would be very few design restrictions that you actually have, because I was telling you before, you could do like very sophisticated key splits on the keyboards for sampled sounds. There'd be essentially no limit except memory, of course. At some point you run, even if you have 32 megabytes, like you probably know what your rampler or sampler has of memory. Eventually you run out if you're too crazy, right? But it was still better than anything that you have before. The thing, one of the bad things, at least I think, is of course the mixing routine, where I showed previously that I re-implemented. It was rather slow and a bit noisy. And if you want to know details about that, listen to my last year's Winter ICMP talk. It would still, I mean, even though it had some authoring tools available, you wouldn't have, like, what I mean by that is you wouldn't have to, like, write the data definitions in your C files. I mean, there were some tools available, but it was still not great. Like, there were no GUI programs or anything available for sound designers who don't care about programming. And that's the last point is important for me as someone from the ROM hacking community. this workflow really doesn't integrate well into modern DAWs, because really the original tool mid2AGB that would convert the MIDI files into the MP2K format, it would really be finicky about what exact events that you use, and it will only allow certain types of events for certain features. And at least that the thing that I found about it is that with today's DAWs, it's sometimes impossible to get it sound right, which is why I also rewrote that tool, which I mentioned previously, I think. So just to give you, for the conclusion, an overview, there were definitely alternatives being developed. I mean, especially considering the ugly downsides. And of course, we had our standard Music Player 2000, and there was, interestingly, a variant from Pokemon, which was mostly identical, but they added compression support for compressed sample data, which would be important because they have, like you in GBA games, how many Pokemons do you have? Like 300 something, quite a lot. And you'd have to like save these cry data, so the noises that the Pokemon make, and that would be quite a lot of the data chunks in those games. So this is why they added compression support. And Camelot, which I also talked about last year, they also did a modification of this engine with higher quality and like very basic synthesizer support. Metroid games, ironically developed by Nintendo, they also developed a higher quality variant, but this was in a rather late year of the GBA. So I believe that's one of the reasons why it didn't really make it into the official SDK. And from what I know, the engine in this variant was almost completely rewritten, but the data formats were I think mostly compatible. And there were also other like completely different sound engines. For example, Krawall, which, I mean, if you're German, you might know what this means. This one was, I think, like a tracker-based music engine. And there's also GAGS, which would be, I think it's an in-house engine. Essentially what it would mean that you would record your music files, you would send it off to their studio, and they'd give you the binary object files that you put in your game. So they were really obscure about what they were doing. I think by now this has been reverse engineered, but I personally have never really looked at it in that much detail. There's also Musics, but I don't personally know much about it. Okay, now that's that. Of course, now we've discussed the hardware and software. And for me, also, an always interesting topic was, how do you emulate it? Well, emulation, I mean, sounds simple first because there are Game Boy Advance emulators available, right? But I'm thinking it out of a context, like how do you actually just listen to the music? Because if I want to listen to this specific track of the game, I don't want to go into the game, walk to the position and do whatever, right? So people came up with this solution, and I'm not sure exactly when Highly Advanced was first created, but essentially what it would be is an emulator that runs inside your music player. In this specific case, it was Winamp, so you know which era it's from. And essentially what they do is you'd create these GSF files, which would be essentially ROM images where you basically strip everything out besides the sound, and then add some metadata to it to know where exactly all the song positions are, and then you'd load it into your music player and would be able to listen to emulated music in Winamp. I mean, today I think there's a very popular Fubar 2000 plugin for the Linux world, Audacious on Mac. I'm not sure which. I'm sure there's some option. So this would be the obvious choice if you want to have accurate music. So as in that you would get exactly the same type of ugly noises that the hardware produces, assuming that the emulator is somewhat accurate to hardware. Another thing that personally interested me more were interpreters. So that would essentially do high-level emulation because they are agnostic of the data format used by the Music Player 2000. And this was one of the first tools that I came over, like it's called SAPI. It's also frankly enough, why some people call this sound engine the SAPI engine, even though I think it's this is just because the tool was called like this. And I think this is also more than 20 years old. But it still works on the modern Windows, which I think is pretty cool. And there were some refinements to this tool. Unfortunately, this version from 2005, I couldn't get to work on Windows 11 anymore because thank you, Visual Basic. But frankly enough, the 2006 edition still works, although I'm not sure because this is not the original SAPI 2006. This is a modification that some people from Japan, I think, have done. Unfortunately, I don't know who it was. Which still works on modern Windows, which I think is pretty cool. But as in sound accuracy, the first SAPI that you saw, this was MIDI only, so no samples or anything. Like this SAPI 2006, this would support sample playback, but it would still be pretty, well, at least out of my view, not very accurate. Like the timing would be off, the reverb wouldn't sound right, and a few other issues, and some issues with volume scaling. Which is why I wrote my own tool called AGB Play, which you can find on my GitHub page. And one of the goals that I had with AGB Play is to have really high quality playback. So high quality in the sense of playing back these sound tracks at a quality that they were really never intended to be heard. So because I don't have to go through the hardware, I don't have to deal with the noise, I can do everything with floating point accuracy and that stuff. And I really encourage you, if you like Game Boy Advance soundtracks and you want to listen to it, try out this tool. It's open source. You essentially just compile it, put it in a ROM file, and it scans everything. And it supports most games. I think the scanner still has some issues with some games. But if you find issues that games are not supported, open up an issue and I'll try to fix it. And actually now, because we still have at least a little bit, I can just give you a short demo here. So what this would be looking like, I have currently Final Fantasy loaded in here. Let's see here, play back the battle theme. Yeah, unfortunately some sound issues in the game. And one of the nice things that you can do with this tool if you're a musician is that you want to practice something, you can slow it down as much as you want with these buttons at the top. And make it easier to play for you, or just listen to single tracks. And one thing that was at some point really obvious to me is, well, I mean, we can use it to rip music from the game. And this is why there is like an export engine. You can export individual tracks to your heart's content. So, and this is really where I want to say a bit of special thanks to a couple of people that have influenced me during my work. Brekelat from the rumhacking.net community. He's written this cool zappy.txt file, which documents the music format. Like today, it's not super up to date anymore, but it was really the first document that I found which described this engine very accurately. To those two guys whose names I don't know how to pronounce, that created Zappy, even though I have kind of a love-hate relationship with Zappy because it would be a very unreliable program. To this person here who would be very diligent with feedback for AGB Play, and of course those two people here who created ZapTapper, which is a GSF ripping tool. So GSF file, the files that you use to load music into your music player's emulator. And just a general thank you to the very cool GBA dev community and the HCS64 community who do things like a lot of work regarding video game music, essentially. If you want to find my email and contact, check out my GitHub page or any of my projects. Thank you very much for coming. So I think we still have a tiny bit of time for a question. So if anyone has one, go ahead. Essentially, if you don't have any questions, feel free to talk to me afterwards. I'm here the next 3 days, so even if it's just nothing related to this specifically, or Game Boy Advance, or Nintendo DS in general, I'm open for questions. Okay, no more questions? That's also okay. So then, thank you, and see you.